Hey fellow nerds, today we are going to start signals and systems with introduction to signals. We will learn classification of signals, representation of signals, and basic operations on signals. But first of all, we have to understand what are signals. As it is written over here, it is a mathematical function of one or more variables that carries certain information about some physical phenomenon. For example, when I'm talking to you, you're listening to my voice. My voice is changing with respect to time. So we could say that it is a function of time. The variable is time. And it is certainly containing some information because I'm telling you stuff. So speech signal is an example of a signal. Now let us classify signals into two broad categories. The first one is continuous time signals. Continuous time signals are defined for all values of t. So as you can see over here, this is an example for continuous time signal. We can also call this analog signal. Its independent variable, which is t, time, is continuous, and it is denoted as x of t like this. Now, the question is, what if my signal looks like this? Is this still continuous or is it discontinuous? Well, it is actually discontinuous mathematically, but this is considered to be continuous time signal because the condition for a signal to be continuous is that it is defined for all time t. Let us take a closer look at this signal. You can see it is defined for all values of t. It starts from here, it goes all the way, and it reaches over here. So it is defined everywhere, which basically makes it a continuous time signal. The second class of signal is discrete time signal. You can see it is denoted as x of n. Obviously, t has become n here, but another change you can see is that we are not using these brackets anymore, we are using this. Now, these kinds of signals are defined only for integer values of n. What you can see over here is an example for a discrete time signal. So at 0, the value is 0. At 1, you have some value. At 2, you have some other value. At 3, you have another value. At 4, you have another value. It goes on like that. On the negative side also, you can have different values. But you can see not every number n has a value, right? If I take this point, you can see the signal is not defined. So this is a discrete time signal. Its independent variable, which is n, is discrete. We can actually derive discrete time signals from a continuous time signal by a method that is called sampling. So first we take a continuous time signal, we pass it through a sampler which does sampling, and then we get discrete time signal, which later we can pass through a quantizer which does quantization and gives us digital signal. Now, the quantization part is actually out of the scope of this course, but obviously we'll be learning about sampling because sampling is the method by which we get continuous time signal converted into a discrete time signal. Let us see how this can be done. Let us see what is sampling. What you can see over here, first I have given x of t, which is a continuous time signal. It looks like this. And what I have done is I have sampled it at particular intervals. That is, I took its value at 0, and then here, and then here, and then here. I also took it here, here, and here. And then I mapped it over here on this graph. So at 0, I got x of 0. At 1, I got x of 1. At 2, I got x of 2. Then I got x of 3. Similarly, on the other side, I have x of minus 1, minus 2, and minus 3. So what I have got over here is a discrete time signal. So basically what I did is I converted a continuous time signal x of t into a discrete time signal x of n by a method called sampling. Now let us move on to representation of signals. First, we will deal with continuous time signals. There are different ways of representing the same signal actually. The first one, let us say as a waveform. So I have x of t and t on y and x axis respectively. Let me define a signal that looks like this. This is my signal. This is one way of representing it. Now, how can we mathematically define it? As you can see, what I have over here is e raised to minus t, right? This is the function, this is the graph of e raised to minus t. And on the other side, what do I have? I have e raised to t. This is e raised to t. So e raised to t on one side, e raised to minus t on one side. If I want to define this mathematically together, I can write x of t is equal to e raised to minus modulus of t. And this is true for every value of t. So I will write minus infinity less than t, which is less than infinity. So every value of t has been considered. Now, the same signal can again be written as a lookup table, which basically means I can define the function like this. X of t is equal to e raised to minus t when t is greater than 0. It is equal to 1 when t is equal to 0. It is equal to e raised to t when t is less than 0. So this is another way of representing the same signal. Let us see how we can define discrete time signals now. The first one, let's take functional representation, that is as a function of n. Let me write an example. Let's say my x of n is e raised to minus 2n. So x of 0 will be e raised to minus 2 times 0, e raised to 0, 1. X of 1 will be e raised to minus 2 into 1. So it goes on like that. I can find out all the terms from the representation. So x of 0, e raised to minus 2 into 0, e raised to 0 is 1. Okay. X of 1 is e raised to minus 2 into 1, so that is e raised to minus 2. X of 2, e raised to minus 2 into 2, so x raised to minus 4. And on the other side, x of minus 1, e raised to minus 2 multiplied by minus 1, so e raised to 2. Again, e raised to minus 2 times minus 2 will be x of minus 2. So e raised to 4. So it goes on like that on both sides, right? Let me put this in a bracket. This is also my x of n. But now, the problem with writing like this is that I don't know which is the 0th term, right? I don't know which is the first term. I don't know which is the second term because it is not mentioned anywhere over here. If you show someone this, how will they know which one is which term? So we have to mention that. For that, what we do is we just put an arrow at the 0th term. So arrow shows origin. Now, if you show this to someone, they will directly know 1 is the 0th term, first term is e raised to minus 2, e raised to minus 4 is the second one, and it goes on like that. On the other side, e square is minus 1 and e raised to 4 will be minus 2. Now, over here, the third method is graphical representation, which we have already seen. So, as you can see, at 0, we have this much. At 1, we have this much. At 2, we have this much. At 3, it is going like this. And on the other side, minus 1 has this, minus 2 has this, minus 3 has this. It goes on like that. So, graphical representation of a discrete time signal is also possible. Now, for this as a lookup table, we have seen earlier how we can define a continuous time signal using a lookup table. We can do the same here also. Let's write an example. Let us say my x of n is 1 when n is greater than or equal to 0 and it is 0 when n is less than 0. How about we solve a problem now? The question is x of t is given. X of t is half e to the power minus 0.5 t. And we have to calculate the discrete time signal if fs is 10 Hz. Here fs means sampling frequency, from which we can actually write the value of sampling time period. Ts will be 1 by fs, 1 by 10, so I can write 0.1 seconds. So basically when they say calculate discrete time signal if fs is 10 Hz, that is ts is 0.1 second, what it means is that you have to sample the continuous time signal that has been given in the question at every time interval 0.1 seconds. To understand that better, let us take a random signal. Let's say this is my signal. This is my continuous time signal, and I have to create the discrete time version of this with a sampling frequency 10 Hz. That is, my sampling time period is 0.1 seconds. So what I have to do is I will take the sample at t equal to 0, then I will take t equals 0.1, and then I'll take t equals 2 times 0.1, that is 0.2, then 3 times 0.1. On the other side, I will take minus 0.1, minus 0.2, minus 0.3. In a general sense, we can say that I will take sample at 0, ts, 2ts, 3ts, like that. and on the other side minus ts, minus 2ts, minus 3ts, like that. And x of t is given, right? So let us write the discrete time signal. What will be the zeroth term? X of 0. X of 0 will be the sampled value of my original continuous time signal at t equal to 0. Since x of t is given, to find out x of 0, I can just give the value of 0 to t. So I will get half e raised to minus 0.5 multiplied by t will become 0. Similarly, if I want x of 1 in the discrete version, it will be half e raised to minus 0.5. Instead of t, what will I give? I want the sample at ts. We do have the value of ts, but right now I'm just going to write ts. Right. If I want x of 2, I will write half e raised to minus 0.5. What do I want? Sample at 2ts. So multiplied by 2ts. If it goes on like that, let me ask you what will be the nth term, x of n. I will write half e to the power minus 0.5. What will I multiply it with? Nth term will be the value of the continuous time signal when time is nts. So here I will write n ts. Now let's introduce the value of ts. We know ts is 0.1 seconds. So I can write this as half e to the power minus 0.5 multiplied by n multiplied by ts, which is 0.1. We can write our final answer now. X of n, the discrete version of this signal, is going to be half e raised to minus 0.05 n. Now let us move on to classifying signals into even and odd. Signals are called even if x of minus t is equal to x of t. In the discrete version, if x of minus n is equal to x of n, then it will be called even. So it is going to be symmetric about vertical axis. So whatever we get here should exactly be whatever we get here. That is, x of 1 should be equal to x of minus 1. You can see they are equal here. You can see that is the case in this x of n example also. What do we have here? At 1 we have this value, at minus 1 we have the same value. At 2 we have this value, at minus 2 we have the same value. So this signal is also even. And obviously, if a signal is even, it will be symmetric about vertical axis because on both sides we want the exact same values. For a signal to be odd, x of minus t will be equal to minus of x of t. And in the discrete version, x of minus n will be minus of x of n. What you can see over here is an example of a continuous time signal, which is also an odd signal. On the positive x-axis, this is what we have, and on the negative x-axis, this is what we have. Obviously, x of minus t is the negative of x of plus t, and this is an odd signal. Over here, we can see a discrete time signal. What we have on the positive side is these two numbers, and what we have on the other side is the negative of those. So this is also an odd signal. Now, there is something that is very interesting about odd signals. We know that x of minus t should be equal to minus of x of t. Let us see what will be the value of this function at t equal to 0. That is, if I give t is equal to 0, then I'll get x of minus 0 should be equal to minus of x of 0. But minus 0 is the same as 0, right? So I can write x of 0 should be equal to minus x of 0. Now this is only possible when x of 0 is equal to 0, right? If x of 0 is 1, will it be equal to minus of 1? No. If x of 0 is 2, will it be equal to minus 2? No. If x of 0 is 0, will it be equal to minus 0? Yes. So x of 0 for an odd signal has to be 0. In the discrete version also, x of 0 is going to be 0. Now, something else that will be very fascinating to you is that x of t, which can be any continuous time function, can be expressed as a sum of two odd and even components. That is, if you have an x of t, which is any continuous time function, you can write it as a sum of one even function and one odd function. Let us try to prove this. There is some x of t, which is the sum of an even function xe of t and an odd function xo of t. We have already defined even and odd functions. So xe of t, since it is even, should be equal to xe of minus t. This is the definition for an even function. Similarly, xo of t, since it is odd, will be equal to negative of xo of minus t. We have already written here that x of t is xe of t and xo of t. In that case, x of minus t will be xe of minus t plus xo of minus t. We changed all the t's to minus t. But then xe of minus t will be the same as xe of t because xe means it is an even function. Xo of minus t, since it is odd, will be minus xo of t. So this is what we get here. Let's call this one equation number 1 and this one equation number 2. Now if you add these two equations, on the left hand side you get x of t plus x of minus t. On the right hand side we have xe of t, xe of t, they get added. So there are two xe of t's, and then there is xo of t minus xo of t, they get cancelled. Therefore from here we can write xe of t, that is the even function, is x of t plus x of minus t whole divided by 2. Similarly, if we take equation number 1, subtract equation number 2 from it, on the left hand side x of t minus x of minus t. We have x of t minus x of minus t. On the right hand side there is xe of t minus xe of t, they get cancelled. Xo of t minus minus of xo of t, they get added up. We get 2xo of t. From here we can write what is xo of t. It is simply x of t minus x of minus t divided by 2. So what we have just found out here is that the two components, one being even and one being odd, can be found through these equations. The even component will be x of t plus x of minus t divided by 2. The odd component will be x of t minus x of minus t divided by 2. Let us see if this is true using an example. I have an x of t here. This is a continuous time signal. And from the proof, we know xe of t is x of t plus x of minus t by 2, and xo of t is x of t minus x of minus t by 2, which technically means we also need to draw x of minus t. And what is x of minus t? In x of minus t, whatever happened on the right hand side of the vertical axis in x of t will happen on the left hand side. Whatever happened in the left hand side in x of t will happen in the right hand side. So x of minus t will look something like this. This will be 0, this is 1, value is minus 1, this is minus 1, and this is 2. Now let's try to find out the even component. Even component is x of t plus x of minus t divided by 2. So on this side, x of t has 2, x of minus t has 1. We have to add them. So 2 minus 1, we will get 1. But then we also have to divide it by 2. So on the right hand side, we get half. How about the left hand side? For x of t, we have minus 1 here. For x of minus t, we have plus 2. If we add both of them, again 2 minus 1, we get 1. Then we have to divide it by 2. So again we're getting 1 by 2. So over here also we get the same. Now let's try to figure out the odd component, for which we want x of t minus x of minus t divided by 2. On the right hand side, x of t is 2, x of minus t is 1. We need x of t minus x of minus t. That is 2 minus minus 1. 2 plus 1, 3. Then 3 has to be divided by 2. So we're getting 1.5 on the right hand. So on the right hand side, it kind of looks like this. 3 by 2. On the left hand side, x of t is minus 1. X of minus t is plus 2. What we want is x of t minus x of minus t. That is minus 1 minus 2. That is minus 3. And then we have to divide it by 2. So what we get on the left hand side is minus 3 by 2. So over there it looks something like this. Minus 3 by 2. So these are the odd and even components. Let's go back to the definition. X of t can be expressed as the sum of two odd and even components. So if these are the correct odd and even components of our x of t, that means if we add them together, we should get our original signal. Let us see if we get that or not. So I have xe of t here, I have xo of t here. If you add the right hand side, we have half here, we have 1.5, 3 by 2 here. If we add both of them, what are we getting? 2. On the other side, here we have half and here we have minus 1.5. If we add both of them, minus 1.5 plus 0.5, we get minus 1. So we get minus 1 here, which is actually the original signal that we started with. Now, this is actually true for discrete time signals as well. X of n can also be expressed as the sum of two odd and even components. And the even component will be x of n plus x of minus n by 2. And xo of n is going to be x of n minus x of minus n divided by 2. I am not doing the proof again. It is exactly the same. You can try it yourself. But let us see an example. The discrete time signal that we're taking here as an example is given, it has value 1 for all n greater than or equal to 0 and it is 0 for all n less than 0. You can see the graphical representation over here. From 0 to the right side we have 1, to the left side we have zeros. Obviously, to get the even and odd components we need x of minus n as well. X of minus n will be exactly the opposite. It will have 0 for all n greater than or equal to 0 and it will have 1 for n less than 0. So over here you can see we have 0 for all these values of n and we have 1 for all these values of n. To get the even component, we have to first add x of n and x of minus n and then divide by 2. So if we add all of these, on the right hand side here we have ones, here we have zeros, so we'll get 1. Here we have zeros, here we have 1, so sum will be 1. So we have entirely 1, but then we have to divide it by 2. So the even component is half everywhere. For the odd component, we need x of n minus x of minus n divided by 2. X of n has all of these. We have to subtract all of these. So that means from 0 to the right side, we will have 1. From minus 1 to the left side, we will have minus 1 since we are subtracting this. But then we have to take divided by 2 as well. So xo of n, the odd component, will have from 0, 1, 2, 3, all these points, we will have 1 by 2, positive 1. On the left hand side, for minus 1, minus 2, minus 3, etc., we will have minus 1 by 2. Now let us check if this is correct. How do we check it? We'll try to add the even and odd components and check if the original one comes out or not. So we have xe of n, we have xo of n, and then we have x of n. So xe of n has half everywhere. Xo of n has minus half here and plus half here. So if we add these, on the left hand side, plus half, minus half, they all get cancelled. From 0, we have halves, and here also we have half. If you add all of these, you get 1 entirely. And this is actually our original discrete time signal. So yes, this did work. Now let's move on to periodic signals and non-periodic signals. Periodic signals are the signals that satisfy the relation x of t is equal to x of t plus t, which basically means after a time period t, the signal repeats. So the smallest value of t that satisfies the equation, that is the smallest time interval after which the signal starts repeating, is called the fundamental time period. If you want the fundamental frequency, you can take the reciprocal of the time period and you will get that. If you want angular frequency, you just write 2 pi by the time period, or you can also write 2 pi multiplied by the frequency. The same can be defined for a discrete time signal as well. For a particular n, the signal can repeat, making 1 by n the fundamental frequency. If you want fundamental angular frequency, you can write 2 pi divided by n. Now, non-periodic signals are obviously the signals that do not repeat after a particular time period. Obviously, this one is not repeating anymore, so it is non-periodic. And this one is also, you can see it's not repeating, so it is also non-periodic signal. Next, we'll move on to a very important property of a signal, which is energy. Let us say you have a continuous time signal x of t or a discrete time signal x of n. We can actually define the energy of the signal over a particular time period between t1 to t2, or you can also define it over an infinite time interval, that is from minus infinity to infinity. So in the first case, for a continuous time signal, you can write energy is equal to, from t1 to t2, you have to integrate x of t, take its mode, square it, and then integrate from t1 to t2. This will give you the energy of the signal between t1 and t2. In case of a discrete time signal, instead of integration, we will have summation, because in discrete we have discrete values. It is not continuous, so we do not integrate, we take summation. So we will take summation and can take values from sum n1 to n2. We will take modulus of x of n, then square it. Over an infinite time interval, I will define it as a infinity. This will be only differences, you will be integrating from minus infinity to infinity instead of t1 to t2. So integral minus infinity to infinity x of t square dt. The same way we can define for discrete time as well. We'll be taking summation from minus infinity to infinity mod of x of n whole square. Another important property of a signal is the power. Power also can be defined between a time interval t1, t2. For discrete, it will be between n1 and n2, or over an infinite time interval. Now, we know power is actually the time average of energy. So we can easily write power. You have to take energy, integral t1 to t2, mod of x of t whole square dt, then divide it with the time interval. Time interval is t2 minus t1. Now, for a discrete time signal, I will do the same. I'll take the energy, summation from n equals n1 to n2, x of n whose mod has been taken and is squared. Now, obviously, I will divide it with the time. So I will have n2 minus n1 plus 1. Now the question arises, where does the plus 1 come from? To understand that, let us take an example. Let us say I have a signal and I am taking its values from 0 to 3. So 0, 1, 2 and 3 are there. So over here, my n1 is going to be 0, n2 is going to be 3, right? What is n2 by n2 minus n1? 3 minus 0, that is 3. But is 3 the number of terms I have taken? No, I have taken 1, 2, 3, 4 terms. So to get the total number of terms I have taken, I should take n2 minus n1 plus 1, that is 3 plus 1. I should take 4. So when you're dividing here, it shouldn't be 1 by n2 minus n1, it should be n2 minus n1 plus 1. We can define the same thing over an infinite time interval. The only difference that is going to happen is t2 to t1 or n2 to n1 will be minus infinity to infinity. So for continuous time signal, I can write limit t tends to infinity 1 by 2t integral from minus t to t mod x of t whole square dt. Why did I give limit here? Because here I am giving t2 minus t1, right? T2 is my upper limit, t1 is my lower limit. Over here my upper limit is infinity, lower limit is minus infinity. So I should be writing like infinity minus minus infinity to infinity. That's weird, right? We don't write like that. We don't add infinities and all. So what we do is we apply limit. So I integrate from minus t to d, okay, and t tends to infinity. So what will be here? Upper limit minus lower limit, t minus minus t, that is t plus t, that is 2t. So instead of writing my infinity minus infinity, which is absurd, we use limit. The same way we can write power for a discrete time signal. We will write limit n tends to infinity 1 divided by 2n plus 1 summation n equals minus n to n mod of x of n squared. Lower limit is minus n, upper limit is n, and n tends to infinity. 1 by n2 minus n1 plus 1 becomes what? 1 by n2 is n, n1 is minus n, so n minus minus n plus n, then there is a 1. So this becomes 1 by 2n plus 1, which is what we have here. Now, depending on the value of energy and power of a signal, we can actually classify signals into three. A finite energy signal will have finite total energy. Its total energy is going to be a finite value. But for a finite energy signal, its average power is always going to be zero. Let me show how. So let us say E infinity of a particular signal. It is given by integral minus infinity to infinity mod of x of t square dt. And we know power is given by limit t tends to infinity 1 by 2t integral minus t to t mod of x of t whole square dt. But this whole thing basically is just infinity. So I can write this as limit t tends to infinity e infinity divided by 2t. Now let us consider x of t is a finite energy signal, which basically means E infinity here is finite. So if E infinity is finite, then what does this become? This becomes limit t tends to infinity, something finite divided by 2t. So something finite, let's say it is 6. 6 divided by 2 times t tends to infinity means this whole thing tends to become 0. So we can say P infinity tends to become 0 in this case. So for every finite energy signal, its energy is going to be finite and its power is going to be 0. How about we take an example? So our example is this particular signal over here, which is 0 on the negative side, 1 from 0 to 1, and then again 0 after 1. I am going to calculate the energy first. So I have to integrate from minus infinity to infinity mod of x of t whole square dt. But you can see the signal is 0 until 0 and after 1, which means I only have to integrate from 0 to 1 actually. So I will integrate from 0 to 1. Value of the signal x of t is just 1 there. So 1 square dt. Integral dt is t. So t from 0 to 1 is just 1. So technically what we got is energy of this particular signal is finite. How about power? Power is given as limit t tends to infinity 1 by 2t integral minus infinity to infinity mod of x of t whole square dt. Or I can just write limit t tends to infinity 1 by 2t. What is the rest? Wait, I don't have to write infinity here. I can just write minus t to t because t tends to infinity has already been mentioned here. Yeah, so 1 by 2t multiplied by e infinity. This whole thing here is just energy only. But then we just found e infinity is 1. So this is limit t tends to infinity 1 by 2t. So we have 1 by 2t, but t is a very large value. T is very close to infinity. That means this thing is very close to 0. Power becomes 0. This is an example of a finite energy signal. Now the second kind of signal is a finite power signal. This one will have finite average power, but it will have infinite total energy. Let me show you how. So power over infinite time interval is given by limit t tends to infinity 1 by 2t integral from minus t to t mod of x of t whole square dt. Energy is limit t tends to infinity integral from minus t to t x of t whole square dt. But this can also be written as p infinity multiplied by 2t. So I can write e infinity is 2t multiplied by p infinity. But for a finite power signal, we have p is finite. If power is finite, then what is e? It is 2t times p infinity, but t tends to infinity. So we can conclude for a finite power signal, it is defined as a signal with finite average power. But if a signal has finite average power, as we just saw, it will also have infinite total energy. Let us see an example for a finite power signal. So this is a discrete time signal. It is given as x of n is 4. That is, it has the value 4 for every value of n. X of 0, 4. X of 1, 4. X of 100, 4. X of minus 1000, 4. Let's try to calculate energy of this signal. So energy is given as limit n tends to infinity. I have to take summation from n equals minus n to n x of n squared. But here x of n is 4 for all values of n. So 4 square is simply going to be 16. So I can write limit n tends to infinity summation n equals minus n to n 16. 16 is a constant. How about we take it out? So limit n tends to infinity 16 summation n equals minus n to n 1. So technically what I get here is limit n tends to infinity. There is 16 multiplied by 2n. So what we have is 32n, where n is a huge value which tends to be infinity. So this whole thing becomes infinite. That is, the energy of this particular signal given over here as an example is infinite. Now let's try to calculate the power as well. Power is given by limit n tends to infinity 1 by 2n plus 1 summation n equals minus n to n x of n whole square. X of n is 4 everywhere, squared, I get 16. The same thing will happen here also. I have limit n tends to infinity. There is a 1 by 2n plus 1. There is a 16 which is constant. And then I take the summation. I will get 2n just like I got in the previous case while finding energy. So this is limit n tends to infinity. 16 is a constant. How about I write it here? Then I have 2n divided by 2n plus 1. I am going to divide the numerator and denominator of this part by 2n. What do I get? 16 limit n tends to infinity 2n by 2n 1 divided by 2n by 2n 1 plus 1 by 2n. Limit n tends to infinity 1 by 1 plus 1 by 2n. What happens to 1 if n tends to infinity? Nothing. 1 is still 1. What happens to this one? Nothing. What happens to 1 by 2n? 1 by 2n, n is a huge value which tends to infinity. So this whole thing becomes 0. So I can simply write this is 16 multiplied by 1 by 1 plus 0, which is just 16. So power of this particular signal is finite, right? So x of n equal to 4, which is a discrete time signal, has finite power and infinite energy. So this is an example for a finite power signal. Now the third kind of signals is a neither energy signal nor power signal. These kind of signals are neither energy signals nor power signals. That is, their energy is not finite, their power is also not finite. We'll see an example of this. X of t is equal to t. Let's calculate its energy. Energy will be limit t tends to infinity integral minus t to t. I have to take the square of it. So limit t tends to infinity. Integral t square is t cube by 3. Limits are minus t and t. So this is limit t tends to infinity. T cube by 3 minus t cube by 3. They get added. So 2t cube by 3. So t tends to infinity and we're taking t cube. So obviously this whole thing is going to be infinite. Let us try power as well. Power is given as limit t tends to infinity 1 by 2t integral from minus t to t x of t whole square is t square dt. Integral t square is t cube by 3, so this becomes limit t tends to infinity 1 by 2t t cube by 3. We have to apply the limits from minus t to t. That is limit t tends to infinity 1 by 2t t cube by 3 minus t cube by 3. They get added. We get 2t cube by 3. 2 and 2 can be cancelled. 1t can be cancelled. What we get is limit t tends to infinity t square by 3. That is, t is a huge value which is very close to infinity and we're taking square of it. So this is also going to be infinite. So for this particular signal, which is a continuous time signal, x of t equal to t, its energy is infinite, its power is also infinite. So it is neither an energy signal nor a power signal. Now that we are done with classification of signals, we are going to learn some basic operations on signals. The first operation is amplitude scaling. We have a signal x of t, we multiply it with a constant c, and we get y of t. C here is called sampling factor. Let's understand this using an example. We have an x of t, which is a triangular signal ranging from -2 to 2, and we are multiplying it with a constant c. Now, when you do that, what actually happens is the amplitude of the signal gets multiplied by c everywhere. So at -2, its original value is 0. 0 multiplied by c is still 0, so we get 0. At +2 also it is 0, so we get 0. At 0 it is 1, so when you multiply it with c, you get c. To get the rest of the values, we can just connect these points. This is pretty simple, but there is something interesting we can see here. Let's take a look at the slopes of these graphs. Over here, we can see the slope is 1 by 2, and the slope is positive, so positive 1 by 2. Over here, the slope is negative, and it is still 1 by 2, so it's -1 by 2. In the new graph, here it is going to be plus c by 2, and here it is going to be minus c by 2. So what we can see here is the slope has also been multiplied by c. That is, we can conclude slope gets scaled by c. Now we will see the area. So area of this triangle is going to be half multiplied by the base, that is 4, into height is 1, and this is 2 units. In the new triangle, it will be half, base is still 4, but the height is now c. So we get 2c. Again, we can see the area has also been scaled by c. Let's write it down. Area gets scaled by c. Now let's do the same thing for a discrete time signal. We have x of n, which is a discrete time signal. We multiply it with c, which is the sampling factor, and we get y of n. Let us say x of n is this -3, -2, 2, 0, 1, 3, and -2 is the 0th term because we have the arrow here. Now, let's say my sampling factor is 2. I'm multiplying it with 2, which means every term will get multiplied by 2. The term that is corresponding to -2 will be the 0th term. So -4 will be the 0th term. -3 becomes -6. 2 becomes 4. 0 is still 0. 1 becomes 2. And 3 becomes 6. The next operation is amplitude reversal. In this case, the sampling factor c will be less than 0, that is, c is going to be negative. For example, let's say I have an x of t that looks like this, a triangular signal. My c is -1. I get this. It is reversed. The same thing happened in discrete time signal also. Y of n is cx of n, but here c is less than 0. Taking an example, my x of n is -3, -2, 2, 0, 1, 3, 2, -2 being the 0th term. My c here is -2. It is less than 0. So -3 becomes +6. It used to be negative, it is positive now, it got reversed as well. And -2 becomes 4, 2 becomes -4, 0 is still 0, 1 becomes -2, and 3 becomes -6. And the term corresponding to -2 is going to be the 0th term. The next operation is taking modulus. So y of t is the modulus of x of t. This is given here. This is our x of t. X of t looks like this. We have to take the modulus. So when we take modulus, we only take the magnitude, that is the positive value. On the right hand side, this is positive already. So we will get the same thing. It will kind of look like this. Right. On the left hand side, we have negative values. We do not take the negative sign, we want the positive. So it will look like this. How about in a discrete time signal? So let's say we have x of n, we're taking the modulus and we get y of n. For an example, x of n is -3, -2, 2, 0, 1, 3. What will be y of n if y of n is the modulus of x of n? We'll take the modulus or the magnitude of every number. Modulus of -3 is 3, modulus of -2 is 2, modulus of 2 is 2, 0 is 0, 1 is 1, 3 is 3. And which one is the zeroth term? Obviously the one that is corresponding to the original zeroth term -2. So 2. Let's move on to the next operation, which is adding a constant. So we have x of t, to which we are adding a constant a, and we get y of t. To understand this, let us see this example. Our x of t looks like this, and we have to find out x of t plus 2. Now what that means is 2 will be added to the amplitude at every point, that is for all values of t, amplitude will be increased by 2. So technically, to get that, I can take the same signal, keep it here, and then add 2 everywhere, which means I'll just shift it upwards by 2 units. So this over here will be 2 units. Similarly, if I want x of t minus 2, what do? I want to subtract 2 from the amplitude at every value of t. So here also, I can take the same signal, keep it here, and then shift it downwards 2 units. So this is going to be minus 2. So we can conclude two things here. First one is, if the constant that we're adding, a, is greater than 0, the signal shifts upwards. If a is less than 0, as we saw in the second case, the signal shifts downwards. Let us see what happens in the case of a discrete time signal. Y of n is x of n plus a. Let's say x of n is 3 minus 2, 1, 1, 0, minus 3, where 1 is the middle term. And I want to find out y of n, which is x of n plus a constant 2. What happens is every term gets 2 added to it. That is, 3 will become 5, minus 2 becomes 0, 1 becomes 3, 1 becomes 3, 0 becomes 2, minus 3 becomes minus 1, and obviously I have to mark the middle term. It will be corresponding to the original middle term 1, so 3 is the middle term. If it is x of n minus 2, then every term will have 2 subtracted from it. The next operation is time shifting. Here we add a constant to the independent variable, which is t. So y of t is going to be x of t plus a. Let's understand this better using an example. So we have an x of t here. It kind of looks like this. Let's try to figure out what is x of t minus 1. If this is x of t, what is x of t minus 1? Let's write down the values of x of t minus 1. When t is equal to 0, what will be x of t minus 1? It will be x of 0 minus 1, that is x of minus 1. At t equal to 1, what will be x of t minus 1? X of 1 minus 1, that is x of 0. At t equal to 2, it will be x of 2 minus 1, that is x of 1. On the other side, when t is equal to minus 1, we get x of minus 1 minus 1, that is minus 2. So you can see what is happening here. There is a pattern. X of minus 1 goes to 0. X of 0 goes to 1. X of 1 goes to 2. Similarly, x of minus 2 goes to minus 1. You can see every value has gone 1 unit forward. Value that we have at minus 1, it will now occur at 0. Whatever we have at 0 will now occur at 1. Whatever we have at 1 will now occur at 2. So technically, I can just take the same function, keep it here, and then move it 1 unit forward, and I have x of t minus 1. Now let's try to figure out what will be x of t plus 1. We have to find out x of t plus 1. So at t is equal to 0, I have x of 0 plus 1, that is x of 1. At t is equal to 1, I have x of 1 plus 1, that is x of 2. At t equal to 2, here I will have x of 2 plus 1, that is 3. On the other side, at t equals minus 1, I have x of minus 1 plus 1, that is 0. Again, we can see a pattern. X of 1 went to 0, x of 2 went to 1, x of 3 went to 2, and x of 0 went to minus 1. So every value has moved 1 unit backwards, which means to get x of t plus 1, I can again take the same function, keep it here. The only thing I have to do is shift 1 unit towards the left. So we can conclude two things here. If a is greater than 0, as you can see in the second case, the signal shifts towards left. If a is less than 0, as in the first case, signal shifts towards right. What if I wanted x of t minus 2? Then the same function, same signal would have moved 2 units towards the right. What if I wanted x of t plus 2? Then this signal would have moved 2 units to the left. Hope you understand. Let's try to do the same thing for a discrete time signal. So y of n will be x of n plus a. We have an example, x of n is 3 minus 2, 1, 1, 0, minus 3, and the 0th term is 1. What is x of n minus 1 going to be? At t equal to 0, I will get x of 0 minus 1, that is x of minus 1. At t equal to 1, I will get x of 1 minus 1, that is 0. At t equal to 2, I will get x of 2 minus 1, x of 1. At t equals minus 1, I will get x of minus 1 minus 1, x of minus 2. The pattern is everything is shifted 1 unit forward. Minus 1 goes to 0, 0 goes to 1, 1 goes to 2, minus 2 goes to minus 1. Here also the whole signal shifts 1 unit towards the right. So I will take the same signal. It has to move 1 unit forward. So like this. The only difference that happens is the 0th term is not 1 anymore. It is minus 2. Similarly, let's try to write x of n plus 1. All we have to do is take the same signal, but right now the signal has to shift 1 unit towards left. Or instead of moving the whole signal, I can just move the arrow from here to here, and this will be x of n plus 1. Conclusion is, if a is greater than 0, signal shifts towards the left. If a is less than 0, it shifts towards the right. Moving on to the next operation, we have time scaling. Here y of t will be x of at. We are multiplying the independent variable, which is time t, with a constant a. For our example, we have a triangular signal ranging from minus 1 to 1. This is x of t. We want to find out what is x of t by 2. Let's try to figure out x of t by 2. At t is equal to 0, x of t by 2, x of 0 by 2, I will get x of 0 itself. At t is equal to 1, I will get x of 1 by 2, x of 0.5. At t is equal to 2, I will get x of 2 by 2, 1. On the other side, if t is minus 1, I get x of minus 0.5. At t equals minus 2, I get x of minus 1. So I am going to take this. At t equal to 0, I am still getting x of 0. Let us say at t equal to 0, our original value was 1. So now also it is going to be 1 over here. Now, where does x of minus 1 go? X of minus 1 goes to t equals minus 2. So let me mark minus 2 over here, and this is where I will get this particular value. Similarly, x of 1 will be at t equals 2. So I have to mark 2, and this is where I will get x of 1, that is this point. So to get the whole signal, I will join them, and this is what I get. We can see the signal has expanded and its duration increased. The duration of the original signal was from -1 to 1, 2 seconds. -2 to 2, here it is 4 seconds. Now let's try to find out what is x of 2t. At t is equal to 0, I get x of 2 times t, 2 times 0, it is still x of 0. At t equals 1, I get x of 2 times 1, 2. At t equals 0.5, I will get x of 0.5 into 2, that is x of 1. On the other side, at t equals minus 0.5, I get x of minus 0.5 into 2, that is x of minus 1. This is all we need right now. So x of 0 is still at 0, so I can mark that point. It is still at 1. Now, where does x of minus 1 come at? X of minus 1 is going to come at 0.5, minus 0.5. So I will mark minus 0.5 here. And where is x of 1 coming? X of 1 will come at 0.5. I need to mark 0.5 as well. To get the entire signal, I'll just join these points. And this is what we get. Now we can see that the signal has compressed and its duration decreased. It used to be 2 seconds, now it is only 1 second. Let's write down the conclusions. If A is greater than 1, signal compresses. If A is less than 1, signal expands. Let's do a similar thing with a discrete time signal. So y of n is x of a times n. For example, we have x of n 3, minus 2, 1, 1, 0, minus 3, and 0th term is 1 over here. First, let's take x of 2n. At n equals 0, I will get x of 2 times 0, I will get x of 0. At n equals 1, I get x of 2 times 1, x of 2. At n equals 2, I get x of 4. On the other side, at n equals minus 1, I get x of minus 2. At n equals minus 2, I get x of minus 4. So at n equals 0, x of 0, I will get 1. At n equal to 1, x of 2. X of 2 here is 0, 1, 2, it is 0. I'll get 0. At n equal to 2, I get x of 4. You can see 0, 1, 2, 3. We don't have an x of 4, so we can just leave it. N equals minus 1, I get x of minus 2. We have 0, minus 1, minus 2. Minus 2 is 3. N equal to minus 2, x of minus 4. We don't have a term at minus 4, so we can remove that also. What we get here for x of 2n is 3, 1, 0. And the middle term, x of 0, is 1. So as you can see, the signal has been compressed. When a is greater than 1, signal undergoes compression. Let's try x of n by 2 now. At n equal to 0, I get x of 0 by 2, which is x of 0 itself. At n equals 1, I get x of 0.5, which is non-existing. So I will take n equals 2, I get x of 1. At n equals 4, I get x of 2. At n equals 6, I get x of 3. On the other side, at n equals minus 1, I get x of minus 0.5, which doesn't exist. So I'll take n being minus 2, which is x of minus 1, and taking n equals minus 4 will be x of minus 4 by 2, which is minus 2. So we can see here n equal to 0 as x of 0, x of 0 is 1, n equals 1, x of 0.5 doesn't exist, so leave it. N equals 2, x of 1, x of 1 is 1, n equals 4, x of 2, x of 2 is 0, n equals 6, x of 3, x of 3 is minus 3, again minus 0.5 is not existing, n equals minus 2, x of minus 1 is minus 2, and n equals minus 4, x of minus 2 is 3. Now we can see that at n equals minus 4, we have 3. Okay, at n equals minus 3, we don't have anything, so we put a 0. At n equals minus 2, we have minus 2. At n equals minus 1, we don't have anything, so we put a 0. Then at n equals 0, we have 1. N equals 1, we don't have anything, so we put a 0. N equals 2, we have 1. N equals 3, we don't have anything, so we put a 0. N equals 4, we have 0. N equals 5, we don't have anything, so put a 0. N equals 6, we have minus 3, and that's all we have. You can see that there are zeros in between all our original terms, and the signal obviously has expanded. So if a is less than 1, signal undergoes expansion. The next operation we have to learn is time reversal. Y of t is equal to x of minus t. That is, whatever happens on the right side for x of t will happen on the left side for x of minus t. Whatever happens on the left side for x of t will happen on the right side for x of minus t. So the new graph will look something like this. 1 will still be the middle term. Over here we get minus 2 and 3. Here we get 1, 0, minus 3. Middle term has to be shown. It's this one. Let's go to the next operation, which is time modulus. Here y of t is taken as x of mod t. Y of t will be x of t for all t greater than 0 and x of minus t for all t less than 0. If this is our x of t, this is how x of t looks like. We have a rectangle here and a triangle here. For t greater than 0, it still has x of t. So I can still draw the same thing over here. Right. For t less than 0, what do we have? We have x of minus t. Let's try to draw x of minus t then. So it will look something like this. Right, this is x of minus t. And what does the definition say? For t less than 0, we have x of minus t. That is, on this side of this signal, we should take reference from x of minus t. What do we have here? We have this. So that's what we're going to have here. We'll have a triangular signal. So we can conclude that when we take time modulus, what happens is whatever was in the original signal on the left side will be gone. Whatever was on the right side of the vertical axis will be exactly what you will have to find on the left side. Let's try to do the same thing for a discrete time signal. Y of n is x of mod n, which means y of n is x of n for n greater than 0 and x of minus n for n less than 0. For example, we have our x of n 3, minus 2, 1, 1, 0, minus 1, 0th term being this 1 over here. I need x of mod n. So what will be x of 0? X of 0 is going to be x of mod 0, which is x of 0. X of 1 is going to be x of mod 1, which is x of 1. Similarly, x of 2 is going to be x of mod 2, which is x of 2. So on the right side, it's exactly going to be the same. On the opposite side, x of minus 1 will be x of mod minus 1. Mod of minus 1 is 1, so x of 1. X of minus 2 will be x of mod minus 2, so x of 2. So it goes on like that. Write the signal. We have 1 at the middle. On the right hand side, we have exactly the same. So 1, 0, minus 3. Now x of minus 1 will be x of 1. That is 1. X of minus 2 will be x of 2. So it is 0. X of minus 3 will be x of 3. That is minus 3. Whatever we have here is exactly what we have here. Now that we have learned all these basic operations on signals, let's try to solve a problem. So we have been given an x of t over here. This is what we have. And first we have to figure out what is 2 times x of t. This is amplitude scaling. When you write 2 times x of t, what happens is the value gets multiplied by 2 everywhere. You can see that the value here is 1, here it is 1, here it is minus 1. So 1 will become 2 and minus 1 will become minus 2. What happens here? It is 0. 0 multiplied by 2 is still 0. What happens here? 0 multiplied by 2, still 0. So what we get will be something like this. is 2 and this is minus 2. Now we have to find out x of 2t, and that's what we call time scaling. We have already done this, we'll do it again. X of 2t, so at t equal to 0, you will get x of 2 times 0, that is x of 0. At t equals 0 0.5, you get x of 2 times 0 0.5, that is x of 1. At t equals 1, you get x of 2 times 1, that is x of 2. On the other side, when t is minus 0 0.5, you get x of minus 0 0.5 multiplied by 2, that is x of minus 1. And when t is minus 1, you get x of minus 2. So technically what happens here is x of 0 is still going to be at 0, but x of 1 goes to 0 0.5, x of 2 goes to 1, x of minus 1 goes to minus 0 0.5, x of minus 2 goes to minus 1. So every number gets halved. So our new graph will look like this. Amplitude doesn't change, it is still from 1 and minus 1. This is minus 0 0.5, this is 0, this is 0 0.5, and this is 1. So what did happen here? Compression. Our signal got compressed. Let's take the same signal again and try to find out what is half x of t. Now, this is again an example of amplitude scaling. Only difference is the constant is less than 1 now. It's half x of t. What happens here? All the amplitudes becomes half. Value of the signal becomes half at every point. So the new graph will look like this. Minus 1, 1, 2, this is 0 0.5 and this is minus 0 0.5. Now let's try to find x of 0 0.5t. This is again another example for time scaling where the constant is less than 1. At t equals 0, I will still get x of 0 0.5 into 0, I'll get 0. At t equals 2, I get x of 2 by 2, that is x of 1. At t equals 4, I get x of 2. On the other side, at t equals minus 2, I get x of minus 1. Again, at t equals minus 4, I get x of minus 2. So whatever happened at minus 1 here will now happen at minus 2. Whatever happened at 0, still at 0. Whatever happened at 1, at 2. Whatever happened at 2, now at 4. So the new graph will look like this. What happened here obviously is an expansion. Signal got expanded. Again, let's take the same signal. What are we doing here? Finding minus x of t. It is the operation called amplitude reversal. We have plus 1 here, it will become minus 1. We have minus 1 here, it will become plus 1. We have plus 1, it will become minus 1. So our graph will look like this. Next, we need to find out x of minus t. This is what we call time reversal. At t equal to 0, I get x of minus 0, which is x of 0, so the same. At t equals 1, I get x of minus 1. At t equals 2, I get x of minus 2. On the other side, at t equals minus 1, I get x of minus 1, so plus 1, or x of t minus 2. So basically, whatever I got on the right side will now be on the left side. Whatever I got on the left side will now be on the right side. And so our graph will look something like this. This will be 1, minus 1, minus 2, and amplitude 1 and minus 1. Now, what we have to do here is, we have the same x of t. We're going to draw x of t plus 1. And the operation we're doing here is adding a constant. We're adding a constant to the amplitude. So, since the constant here is plus 1, 1 will be added everywhere, which means I can take the same signal, place it here. Then to add 1 everywhere, I just have to lift it upwards 1 unit. The next operation we have to do is, we have to draw x of t plus 1. And this is called time shifting. Let's try to write down x of t plus 1 first. At t equal to 0, I will get x of 0 plus 1, that is x of 1. At t equal to 1, I get x of 1 plus 1, that is x of 2. On the other side, at t equals minus 1, I get x of minus 1 plus 1, which is 0. So basically what happens is 0 is now at minus 1, x of 2 is now at 1, x of 1 is now at 0. So the whole signal has shifted 1 unit towards the left. I can again take the same signal, keep it here, and then simply shift it 1 unit towards left. This will be 1, this is minus 1, this is minus 2, amplitude is 1 and minus 1. This will be x of t plus 1. Now let's try to figure out what is x of t minus 1. Here we are subtracting a constant. Or you could say adding a constant, where constant is minus 1. So 1 will be subtracted everywhere. We take the same signal, place it here, 1 has to be subtracted. So keep it 1 unit here. This will be 1, 2, minus 1. Magnitudes, here we have minus 1, here we have minus 2. Now we have to find out what is x of t minus 1. X of t minus 1 is again time shifting. What happens if the constant is negative in time shifting? The signal will be shifted 1 unit towards the right. I will place the same signal. Then I will shift it 1 unit towards right. 1, 2, 3, magnitude 1 and minus 1. We could actually verify this. Let's see, when t is 0, I will get x of 0 minus 1, that is x of minus 1. When t is 1, I will get x of 1 minus 1, that is 0. When t is 2, I will get x of 2 minus 1, that is 1. So you can see that x of minus 1 goes to 0 now, x of 0 goes to 1 now, x of 1 goes to 2. So technically you just have to shift it 1 unit towards the right. How about we plot mod of x of t now? The operation is taking a modulus. Now, when you take a mod of anything, you're basically just taking the magnitude of it and ignoring the sign, which means our signal will now look like this. Next, we have to plot x of mod t. Operation is time modulus. The earlier one was amplitude modulus, now we have time modulus. When you take time modulus, you have to take x of t for all t greater than or equal to 0, and then you have to take x of minus t for all t less than 0. So technically what happens is your graph will be symmetric about the y-axis. Whatever happens over here will be exactly what happens over here. On the positive side, we will get x of t. So it will look something like this. On the negative side, you will get the mirror image of the same thing. So it will look something like this. 1, 2, minus 1, minus 2. Amplitudes are 1 and minus 1. So we have done an example for all the operations we learned. Now the question is, what if we have to apply more than one operation in the same signal? What if I have to find out x of 2t plus 3? There are two operations here. I have a time scaling with the 2 and I have time shifting with the plus 3. So should I do time shifting first and then time scaling, or first time scaling and then time shifting, or does the order not matter? The truth is the order does matter. You can try for yourself. First do the scaling and then do the shifting. In the second case, try doing the shifting first and then do the scaling. And see for yourself if the two signals that you get are the same or different. Well, spoiler alert, they're going to be different. There is an order that you have to follow. That is, first do time shifting, then do time scaling, and then do time reversal. Let us do an example where we have to do all of these. X of t looks like this. What we have to plot is x of minus 3t plus 2. So this 3t corresponds to time scaling, plus 2 corresponds to time shifting. The negative corresponds to time reversal. According to the order that we just learned, we have to do time shifting first, then time scaling, then time reversal. So first I am going to consider the +2, which corresponds to the time shifting. So I will plot x of t plus 2 first, ignoring the -3. So I'll take the same signal, keep it over here, and then shift it 2 units towards the left. 1, 2. So this is our x of t plus 2. According to the order that we just learned, the next step is time scaling. That is, I have to consider the 3 over here. So I will plot x of 3t plus 2 now. That is, I already have x of t plus 2. I have to apply time scaling to it, and the constant is 3. So when you apply time scaling, what happens is the constant is 3 now. So whatever happened at -1 earlier will now happen at -1 by 3. Whatever happened at -2 earlier will now happen at -2 by 3. Whatever happened at -3 will now happen at -3 by 3, which is -1. Also, what happened at -4 will now happen at -4 by 3. So let's mark these points. Let's say this is -1. So -1 by 3 and 2 by 3 will be somewhere around here, and -4 by 3 you can find here. Our graph will look like this. You can see that our signal has now compressed because the constant was greater than 1. The next step is to do time reversal. That is, I will be considering the negative sign over here. So I have x of 3t plus 2. I need to plot x of -3t plus 2. All I have to do is time reversal. And what is time reversal? Whatever happened on the positive side over here will now happen over here. Whatever happened over here will now happen over here. So since we had -1 by 3, -2 by 3, -1 and -4 by 3 here, to do time reversal, I will have to mark positive 1 by 3, 2 by 3, 1 and 4 by 3. The graph will finally look like this. There are some more operations that we can do, like adding two signals together or subtracting one signal from the other one, multiplying two of them together. Let us do some examples of those also. So first, let's consider addition and subtraction. In continuous time, we can write y of t is x1 of t plus x2 of t, and in discrete time, y of n is x1 of n plus x2 of n. For example, let's take x1 of n is 1, 2, 0, -1 and -2, 0 being the middle term. X2 of n is 0, -1, 1, 0, 2, -1 being the middle term. And we're going to add them. Now, one important thing that you have to make sure is that you're adding the corresponding term, which means here 0 is the middle term, here -1 is the middle term. So you have to add both of them. These are the 0th terms. These two are the first terms. These two are the second terms. So when you add, you get y of n, which is the sum, will be, you have a term corresponding to -2 here. We don't have 1 here, so we'll just add 1 plus 0, that is 1. Then 2 gets added to 0, 0 gets added to -1, -1 gets added to 1, -2 gets added to 0, and then there is no third term here, but here we do have a third term, so that will just be 2. Let us do the same thing for a continuous time signal that is given over here. X of t looks like this, and y of t is a triangular signal. We have to add them first, x of t plus y of t. So when you add this triangle and when you add the complement of this, what you actually will get is a rectangular signal. Over here also you are adding this one and then you are adding this one, you will get a rectangular signal. So the sum will look like this. Now let's do subtraction. X of t minus y of t. This is x of t, we have to subtract this from it. If this is -1 second and 1 second, and let's see this is 1 unit and this is also 1 unit, this is -1 second, this is 1 second. Here you have 1 unit, here you have 0 unit. So you will still get 1 unit there. On the other end, at 1 seconds, you still have 1 here and 0 here. You are adding them. So you will get 1. At the middle, here you have 0. So we are subtracting, but still the same because 1, you have to subtract 0 from it. You will get 1. We have 1 here, we're subtracting 0 from it, we get 1. At the middle, here we have 0, we have to subtract 1 from it, so we get minus 1. So let me mark minus 1 over here. This will be our middle point. To get the rest of the points, we can actually just connect the dots. This will be our final signal x of t minus y of t. Now, there is a very interesting thing that you can see over here. The slope of this graph is minus 1 and the slope of this part of this graph is plus 1. If you add both of them, you get 0. And that's actually what you got here. On the other side, this one has plus 1 and this one has minus 1. The sum has 0. It is actually the sum of the other two slopes. We can verify this in the subtraction also. So this one has a slope minus 1 and this one has a slope 1. This is minus 1, that is 1. If you subtract them, you will get minus 1, minus 1, minus 2, and that is actually the slope of this one. On the other side also you can see this is plus 1, this is minus 1. Plus 1 minus minus 1 is plus 2. Are we getting plus 2 slope here? Yes. This side is 2 and this side is 1. So the slope is plus 2. So one thing is very obvious. When you add the signals, their values get added. The slope also gets added. Now let's do multiplication of signals. We can do that in continuous time signals and discrete time signals. For example, we have x of n, 3 minus 2, 1, 1, 0, minus 3, 0 term being 1. x2 of n, 3 minus 2, 1, 1, 0, minus 3, middle term, 0th term being 1. We have to find out the product. We'll call it y of n. Again, we'll be multiplying the corresponding term, the 0th term with the 0th term, first term with the first term, like that. So you can see this will be minus 1 term, this is minus 2. There is no minus 3, but over here we have minus 1, minus 2, and minus 3. So minus 3 will be multiplied with 0, so that is gone. And then 3 will be multiplied with minus 2, we get first one is 0, then we get minus 6. Minus 2 will be multiplied with 1, so we get minus 2. Then the 0th terms 1 and 1 will be multiplied, we get 1. The first terms 1 and 0, we get 0. Second term 0 and minus 3, we get 0. Third term is minus 3 for x1 of n. For x2 of n, there is no third term, so that also is 0. So our signal is technically minus 6, minus 2, 1, where the middle term is 1. Let's do the same for a continuous time signal. x1 of t is given over here, x2 of t is given. We have to find out y of t, and y of t is the product of them. Now at t equal to 0, here we have 3, here we have 2. So 3 multiplied by 2, 6. For t equal to 1, we have 2 here and we have 2 here. So that's going to be 4 here. So I'll mark it 4. For t equals 2, we have 2 here and we have 3 here. So that is going to be 6. Again, let's join the points to get the product. And it will kind of look like this. The next operation we are going to do is differentiation. So let's say we have a signal x of t. I'm going to differentiate it with respect to time, d by dt of x of t, and let's say the resultant is called y of t. So this is our x of t. It's a triangular signal ranging from -1 to 1. Its magnitude at t equal to 0 is a. We are going to differentiate it. Now when you differentiate a graph, what you get is the slope. So from -1 to 0, you will get the slope of this part. From 0 to 1, you will have the slope of this part. Now the slope on this side is a divided by +1 plus a as the slope here. On the other side, it's a divided by -1. So you will get minus a. Now we can write the resulting graph, that is d by dt of x of t. It will look like this. For values, this will be plus a, this will be minus a. Now let's do the opposite of differentiation, which is integration. We have x of t over here ranging from -1 to 1, and I have to plot y of t. Now, when you integrate a rectangular signal over here, you will get a triangular signal with a positive slope like this. And on the other side, it's minus a, so you will again get a rectangular signal, but slope will be negative, -1 plus 1 a. Now, very obviously, we cannot do differentiation and integration for a discrete time signal, but there are two other operations that we can do on them. The first one is finding the first difference. This will be now analogous to the differentiation operation. It is defined like this: delta of x of n is given as x of n minus x of n minus 1. So we will subtract the previous term from a given term. Let's try an example. We have an x of n. It is 1, 2, 3, 4. 1 is the 0th term. So this will be 1, 2, and 3. To find the first difference, let's try to find delta x of 0 first. Delta x of 0 will be x of 0 minus x of minus 1. Here x of 0 is 1. There is no x of minus 1. So we'll get 0. Delta x of 1 will be x of 1 minus x of 0. That is 2 minus 1, which is 1. Delta x of 2 will be x of 2 minus x of 1. So 3 minus 2, that is again 1. Delta x, wait a second, x of 0 was not 0, it was 1. Now delta x of 3 will be x of 3 minus x of 2. X of 3 is 4, x of 2 is 3, so 4 minus 3, again 1. We can write the final answer. Delta x of n will be 1, 1, 1, 1. And we have to mark the 0th term. The next operation we can do here is the first sum. This is equivalent to taking integration on a continuous time signal. We have x of n, which is 1, 2, 3, 4. 1 is the 0th term. Finding the first sum, y of 0 will be x of 0 plus x of minus 1, but we don't have an x of minus 1, so we can just write this is 1. Similarly, y of 1 will be x of 0 plus x of 1. That is 1 plus 2, which is 3. And y of 2 will be x of 0 plus x of 1 plus x of 2. That is 1 plus 2 plus 3. So 6. Y of 3 will be x of 0 plus x of 1 plus x of 2 and obviously plus x of 3. That is 1 plus 2 plus 3 plus 4, and that is 10. We can write our final answer. Y of n is 1, 3, 6, 10, and the 0th term has to be marked. It is 1.